Now, when we look at these are called, by the way, abbreviated electron configurations. Okay. So these are abbreviated electron configurations because we're getting rid of the core, we're abbreviating them. Okay, so let's look at lead again. So lead is down here at number 82. The previous noble gas is xenon, number 54. Not radon. Radon has more electrons. Okay, so it's xenon. So there's the core. And then 6s2, 4f14, 5d10, 6p2. Now, we have to include these two because they're not part of xenon. Okay? Not part. Okay? So we can't just elide them. We can't put them in part of the abbreviation. But they're not really valence, because they're not going to take part in any sort of chemistry. Okay, those are two very full, very heavily resonant subshells. They are not going to participate. They're very happy the way they are. They're not going to do anything. That's why when lead forms ions, when it reacts with nonmetals, it forms a lead 2+ ion or a lead 4+ ion. And that's it. And you can see, looking over here, you have 2s and 2p electrons, and gives you a total of 4. Now I'm going to leave it as a mystery for the moment which one of these gets lost first, which one gets lost second. Does it lose the s electron? Does it lose the p electrons to form lead 2+? Okay, so that is the complication that I wanted to show you for our abbreviated electron configurations. That a full or a half-full subshell doesn't participate in chemistry. So here's iron again. Previous is, argon. Then 4s2, 3d6. So when you look at its orbital filling diagram, then there's 4s2. Then here's 3d6, 1, 2, 3, 4, 5, 6. You can see that this electron here is definitely valence, but the other 5, not really valence. Okay? They're not really going to participate. Okay? They are really heavily resonance. They're really, really happy. They're just going to sit there. You have to show them all, but they don't all participate in the chemistry. Okay? So let's go ahead and look at the electron configurations of ions. Minus config of ions. Okay? This is where we're going to finally, after years of waiting, we're going to answer the question of which electrons does lead lose first. So, lead 2+. Still has the same core, so it's still xenon. And it's 6s2, 4f14, 5d10, 6p2. It's going to lose one of these, 6s or 6p. Which is it going to lose? Well, the weird thing about metals is they always lose their s electrons first. Okay? So lead 2+ is xenon, 4f14, 5d10, 6p2. Okay? S electrons first. And it doesn't matter if you're talking about S versus P or S versus D or S versus F. We'll never talk about losing F electrons because the rare earth metals are kind of ridiculous. But Pb4+, lead 4 is xenon, 4f14, 5d10, and that's it. It's lost now its second pair of electrons, the p electrons, the 6p electrons. Let's go ahead and look at the ions formed by iron. We have iron 2 plus and iron 3 plus. All right, so here is neutral iron, argon, 4s2, 3d6. Okay, so that's the electron configuration. Here's the orbital filling diagram. All right, so that's 4s and 3d. What electrons is iron going to lose in order to become iron 2, the 2 plus ion? Okay. Well, hopefully, that should be obvious now. You lose your s electrons first. So, it's argon 3d6. And now that you know about resonance, you know what electron it's going to lose next in order to form the 3 plus ion. It becomes argon 3d5. So its orbital filling diagram would look like this. 3d, 1, 2, 3, 4, 5. And it has 5 very happy resonating electrons. Okay, so resonance. So now that we have electron filling diagrams, it helps to explain some of the oddities floating around out there that weren't explained before. Now we can explain why the transition metals and the post-transition metals form the various ions they do. It's because of these electron filling diagrams. It's because of quantum mechanics. Now, those were cations. Okay, positive ions equals cations. Positive equals cat ions. Because cats are always happy. That's a lie, but cats make people happy. They're a positive influence. So a negative ion, remember, is an anion. Negative ions are easier to do. Because a negative ion, well, you just look at, say, nitrogen is helium, 2s2, 2p3. They gain electrons until their subshell is full. Okay, so very straightforward. Okay, this is the empty subshell, so it's going to form N3 minus. Still has the same core, but it's 2s2, 2p6. Okay, so anions are really simple. You just fill up the energy level that you're looking at. He, 2s2, 2p6. Okay. Sulfur forms a 2 minus ion, and that is neon, 3s2, 3p6. Nice and straightforward. Adding electrons is always a much simpler proposition than taking electrons away. And now we just have one last little thing to cover. Exceptions. There are a few exceptions to the rules for Aufbau, for filling in your orbitals. These are the only exceptions I expect you to know. Now, the rare earth elements, the F block, those are like nothing but exception. I don't expect you to remember those. These I do expect you to remember. They are chromium, copper, and silver. Chromium is right here. It's element 24. Expect argon, 4s2, 3d4. Copper similarly is argon, 4s2, 3d9. And silver, it's not on the same row, is krypton, 5s2, 5s2, 4d9. All right. Now, maybe some of you might have spotted it already, but these three have a very similar sort of exception and the same reason for that exception. These are what you would expect, and those are wrong. Okay? This is what they actually are. Oops. Copper, chromium, argon, 4s1, it's 3d5. Copper is argon, 4s1, 3d10, and silver is krypton, not 4, 5s1, 4d10. So you can see, hopefully, what's happened. Okay, each one of these took an electron out of the s sublevel and promoted it into the d sublevel. There's a reason why they did that, and there's a reason why they were able to do that. The reason why they did that is very, very simple. Here's S, and here's D. Here's what you would expect for chromium, for example. Chromium has 4 d electrons and 2 s electrons. By pulling this electron out and pulling it over here into the d subshell, suddenly, boom, 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 resonance. Resonance makes electrons a lot happier. It makes them a lot more stable. Okay? So chromium and copper and silver all promote an electron out of the s into the d, because suddenly lots and lots of resonance makes those neutral atoms much, much happier. Now, why are they able to do that? Because although the d subshell is higher in energy, it's not much higher in energy. So the difference between the two subshells is less than the energy you get back from resonance. Okay, so energy of promotion is less than the negative energy of resonance. Okay, so the reason they're able to promote that electron is because they get so much more energy back from resonance. So those are the exceptions. And this explains, for example, why you get the silver 1+ ion, and only the 1+ ion, because it only has the 1s electron to lose. Question for you: why does copper have the 1+ and the 2+ ions? I'm going to throw that question at you and see if maybe you can answer it. But those are the exceptions. Those are what I expect you to remember. The why and the why and the what. Okay? So why do they promote them? Why can they promote them? And what 3 make that promotion? All right, and that does it for Lecture 25. I will see you later.